Inside an internal combustion engine at full capacity, controlled explosions occur hundreds of times per second to drive steel pistons downward. This downward force is translated into rotational motion by the crankshaft, a mass of forged steel spinning at 6,000 revolutions per minute. At these velocities and under these immense compressive loads, any physical contact between the spinning crankshaft and the stationary block produces enough localized friction to destroy the metal. Heat generated by this friction causes thermal seizing, an event where the atomic structures of the metals fuse together, permanently welding the parts in place. The machined iron of the engine block serves as a housing for the specific boundary layer that prevents this catastrophic fusion. The continuous survival of the machine depends entirely on maintaining this invisible barrier. During standard operation, the heavy moving components inside the block never touch. Mechanical reliability at these extreme velocities is dictated by the laws of fluid dynamics rather than solid mechanics. Macroscopic mechanical reliability is sustained entirely by a microscopic pressurized fluid wall. The fluid layer originates at a mechanical oil pump driven directly by the rotation of the crankshaft. A pickup tube draws resting fluid from the bottom sump and into the active system. The pump forces this fluid upward through a filtration matrix, stripping away contaminants that could compromise the integrity of the barrier. The pressurized liquid enters a vascular network of passageways cast directly into the solid engine block. Following a single flow path through this block artery leads directly to the interface of a journal bearing. This hidden network exists to ensure a continuous, unbroken delivery of fluid to every rotating interface in the assembly. This operation requires constant hydraulic pressure to separate the metal surfaces under high compressive loads. A drop in line pressure across this network results in the immediate collapse of the fluid lighter and subsequent mechanical failure. The iron block serves as a rigid vascular framework, dedicated to sustaining the high-pressure fluid moving through it. The journal bearing is the junction where the spinning crankshaft journal meets the stationary block bushing. At this junction, engineers maintain a physical clearance between the two steel cylinders of exactly 0.02 of an inch. A groove cut into the stationary bushing creates a pathway for fluid to distribute itself across the interface. Pressurized oil from the block's internal passages fills this 0.02 of an inch void. This pressurized state constitutes a fluid bearing. Under pressure, the liquid behaves as a structural wedge, forcing the heavy steel components apart and suspending them in a state of zero contact. The rotating shaft floats on a structural liquid wall, isolated from the iron block. The primary load-bearing capacity of the engine comes from the hydraulic resistance of the fluid gap itself. This microscopic, pressurized void is the component that actually supports the mass and force of the engine's rotation. This fluid wall must survive immense mechanical shear forces and the radiating heat of combustion. Thermal gradients naturally cause liquids to thin, which leads to a loss of viscosity. This thermal thinning threatens to collapse the 0.02 of an inch gap. To counter this, engineers utilize viscosity index improvers in multigrade oils, such as SAE 5W30. The 5-weight rating ensures the fluid is thin enough to flow and establish hydraulic pressure during a cold state ignition. The chemical makeup of these improvers includes microscopic polymer coils suspended within the fluid. As operating temperatures rise, these polymer coils physically unspool and expand. This chemical expansion increases the structural density of the fluid, directly counteracting the natural thinning caused by heat. Over time, combustion byproducts infiltrate the system and mechanically degrade these polymers, eventually requiring the fluid to be replaced. Modern motor oil is a dynamic, sacrificial chemical assembly, engineered to maintain its structural properties while resisting the laws of thermodynamics. Observing the engine as a single macroscopic unit reveals the scale of this hydraulic coordination. The internal combustion engine functions as a high-precision, high-frequency reactor. Engineers have achieved the ability to sustain a sub-millimeter fluid gap perfectly through millions of high-heat cycles. This level of engineering aligns with the precision required by ASML lithography machines. ASML systems use extreme ultraviolet light to print microchips, requiring internal components aligned to nanometer-scale tolerances. Both systems rely on the mastery of imperceptible gaps to function at the edge of physical possibility. While semiconductor manufacturing requires precision in a static cleanroom, The engine requires that same precision inside a violent, dynamic environment. Mechanical failure in both environments is a failure to maintain a microscopic boundary condition. Modern industry mass produces these extreme tolerances so consistently that their existence remains unnoticed. Industrial reliability depends on our mastery of the microscopic spaces between the steel.